All right, welcome everyone. So in this video, we are going to define what an orthonormal set is and talk about why such sets are going to be particularly nice when we want to find a basis for a vector space. Finding an orthonormal set for the basis will simplify our calculations in a lot of different settings. So let's first define what an orthonormal set is. So if I have a set of vectors u1, u2, all the way up to vector up, then this is an orthonormal set if it's an orthogonal set of unit vectors. So there's two conditions that need to be satisfied. The first is that all these vectors are orthogonal to other vectors in the set. So if I is not equal to j, then the inner product of ui and uj, that should give us 0. And the second is that each one of these vectors is a unit vector. So that means if I take the inner product of ui with itself, then that equals the magnitude of vector ui squared. And if these are unit vectors, then each of these should give us 1. So I know that the inner product, if I is not equal to j, is 0. And if we take the inner product of any vector with itself, then we should get the scalar 1 back. And so one very nice example that we've seen already is that if I take the set S as the set of all of the elementary column vectors from Rn, then this forms an orthonormal set. So for example, if we were looking at R3, then the set would be E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 would be 0, 0, 1. Each of these vectors does have magnitude 1, so that checks out. And taking the dot product of any one of these vectors with any other vector gives us 0. So this set is an orthonormal set that forms a basis for, in this case, R3, but more generally for Rn. So we would call this an orthonormal basis for Rn. And these are going to be really nice bases to work with. A lot of the formulas that we've just gone through simplify quite a bit when these vectors in our basis are orthogonal with each other, and moreover, when they all have magnitude equal to 1. So for example, we just found a formula for how we can find the orthogonal projection of y onto u, which was given by y inner product u divided by u inner product u. And if we assume now that u is a normal vector, that means a unit vector, I should say, that u has magnitude equal to 1, this denominator just simplifies to 1. So we can find the projection in the case where u is a unit vector by just taking the inner product of y with u. That gives me some scalar, and that's exactly the scalar multiple of u that I need in order to get this orthogonal projection. Okay, so now let's take a look at another nice result from orthonormal sets. So let's imagine we have a set of 3 orthonormal vectors, u1, u2, and u3. So what that means again is that the dot product of 2 different vectors from this set give us 0, whereas taking the inner product of any vector with itself should give us 1 because each of these vectors is a unit vector. And so now let's consider a matrix U that we construct by saying each column of the matrix U is going to be a different one of these vectors from this orthonormal set. And then let's consider what happens when I take the matrix product of the transpose of this matrix U and the matrix U itself. So taking the transpose of matrix U would tell me that the first row of that matrix is U1 transpose. So I'm taking this column vector and rewriting it now as the first row of U transpose. And then the second row is going to be the second column vector transposed. And the third row of this matrix is going to be the transpose of the third column of matrix U. So that's where U transpose we can write as 3 column vectors here. And again, the matrix U that consists of U1, U2, and U3. And now when we take the product of these vectors, we're going to get a bunch of inner products. So I get U1 transpose times U in the first position. Then I would get U1 transpose times U2 to give me the 1, 2 position. And then U1 transpose times vector U3 over here. And we get similar products in each of these entries. And now each of these entries is exactly one of these inner products that we have above. So all of the diagonal entries, these are all going to be 1s from this result up here. And all of the off-diagonal entries, these are all going to be 0s from these results over here. So after simplifying this product, we just get the 3x3 identity matrix. And so looking at this calculation that we've done above, there was nothing special about the fact that I chose 3 vectors from R3. We could have chose n vectors from Rn. As long as all of those vectors together form an orthonormal set, we would get very similar result. So to generalize this, we can state the following theorem, that an m by n matrix U has orthonormal columns if and only if the product of U transpose times U gives us the identity matrix. So here, to summarize this, if I have a matrix whose column vectors together form an orthonormal set, then multiplying the transpose of that matrix and U itself, we're always going to wind up with the identity matrix. Okay, and finally, I want to wrap this up by stating some nice properties of orthonormal sets. So let's let U be an m by n matrix where all of the columns of matrix U form an orthonormal set. Then let's take any vectors x and y that are in Rn, okay, where here n is denoting the number of columns of this matrix U, so that these products are going to make sense. Then that means the magnitude of U times vector x equals the magnitude of vector x. So in other words, multiplying a vector by this matrix U is not going to change the magnitude of that vector. That's a really nice property. Another property is that if I take the dot product, the inner product of U times x and U times y, that is the same thing as just taking the inner product of x and y. And this matrix U does not have any effect on that inner product. And a third property is if Ux inner product with Uy is equal to 0, that is going to equal 0 if and only if the inner product of x and y are equal to 0. So hopefully you can see how this kind of follows from the previous step, the previous property that we've shown. So to kind of summarize what is particularly nice about orthonormal sets is that if we construct a matrix U from those set of column vectors, then multiplying any vector x by this matrix U is going to preserve distances, and it's also going to preserve orthogonality. And these are really, really nice properties when you start to get into looking at computer graphics and other computer algorithms.